In this video, let me consider design of digital filter using bilinear transformation. Design digital filter H of Z. The specifications are given, that is passband attenuation is less than 3.01 dB, passband edge frequency is 500 Hz, stopband attenuation is greater than or equal to 15 dB, stopband edge frequency is 750 Hz and sampling rate is 2 kHz. This filter is to be designed by performing bilinear transformation on Butterworth analog filter. So first let me write the given data. Here passband attenuation is given, that is nothing but Kp. So Kp is equal to minus of 3.01 dB. Kp and Ks are always in minus. Similarly, Ks value is given, that is stopband attenuation greater than or equal to 15 dB, that is minus 15 dB. And here passband edge frequency as well stopband edge frequency are given in Hertz. We supposed to write passband edge frequency and stopband edge frequency in radians per second. Therefore, let me calculate passband edge frequency in radians per second, that is omega p is equal to 2 pi into, here it is 500 Hertz, 500, which gives 1000 pi radians per second. Similarly, let me calculate stopband edge frequency, which is 2 pi into 750 Hz, which gives 1500 pi radians per second. Here the sampling rate is given, that is Fs is equal to 2 kHz. Therefore, I can write T is equal to 1 upon 2000, which gives 0.5 millisecond. Now the first step is to obtain digital frequencies. So digital frequencies are obtained using the formula W, which is nothing but omega, is equal to omega into T. Here this omega is nothing but digital frequency and this is analog frequency. Let me calculate passband digital frequency, that is Wp is equal to omega p into T, which is equal to, so omega p is already calculated, that is 1000 pi into T value is 0.5 millisecond into 10 power minus 3. So solving this, get 0.5 pi. Here 1000 and 10 power minus 3 will get cancelled, will get 0.5 pi. Similarly, stopband digital frequency, that is Ws, is equal to omega s into T. It is nothing but 1500 pi into 0.5 into 10 power minus 3. It gives 0.75 pi. The unit is radians. Now the second step is obtain pre-warp band edge frequencies, pre-warp frequencies as omega p. We can also write it as omega dash p or omega p, both are fine, is equal to 2 by T tan omega p by 2. Substituting the values, here we supposed to consider T equal to 1 second. Let T is equal to 1 second. Therefore, I can write 2 by 1, that is 2 tan omega p is already we have calculated, that is 0.5 pi divided by 2. So simplifying this, we'll get 2 radians per second. Similarly, I will take it as omega dash p or omega p. Omega s is 2 by T tan omega s by 2. Here we can consider same, that T equal to 1 second, that is 2 tan omega s is 0.75 pi divided by 2. So simplifying this, I get 4.5 828 radians per second. Here let me represent pre-warp band edge frequencies as omega dash p and omega dash s, so that I can differentiate omega p and omega s. Now the third step is to design analog Butterworth filter. So to design analog low pass Butterworth filter, we are supposed to calculate order of the filter n. So order of the filter n is given by n is equal to log of 10 power minus 0.1 kp minus 1 divided by 10 power minus 0.1 ks minus 1 whole divided by 2 log omega dash p by omega dash s, that is pre-warp frequencies. Substituting the values, I can write log of 10 power minus 0.1 into 3.01 minus 1 divided by 10 power minus 0.1 into ks value is 15 minus 1 divided by, we have 2 log omega dash p is 2 and omega dash s is 4.828. So simplifying this, we'll get n is equal to 1.91, and we know that it should be rounded off to next integer. Therefore, I can write n is equal to 2. So order of the filter is 2. Now let's calculate the cutoff frequency omega c. The cutoff frequency omega c is given by omega c is equal to omega dash p divided by 10 power minus 0.1 kp minus 1 power 1 over 2n. Therefore, I can write omega dash p is nothing but 2 divided by 10 power minus 0.1 into 3.01 minus 1 power 1 upon 2 into 2, that is n is equal to 2. So solving this, we'll get omega c as 2 radians per second. That is step 4. Now we are supposed to write the transfer function of normalized Butterworth filter for order n is equal to 2. That is transfer function of normalized Butterworth filter for order n is equal to 2. It can be represented. So it is given by h2 of s is equal to 1 upon s square plus root 2s plus 1. So now, therefore, now by applying low pass to low pass transformation to get desired analog filter. So desired analog filter, I will represent it as HA of S, which is equal to H2 of S, provided that S should be replaced by S by omega C. So here cutoff frequency is 2, that is S by 2. So therefore we can write HA of S is equal to 1 upon S should be replaced by S by 2, that is S by 2 square plus root 2 into S by 2 plus 1. So simplifying this, we'll get 4 divided by, it is S square plus 2 root 2 S plus 4. So now applying bilinear transformation to get digital filter. So therefore we can represent h of z is equal to, we have ha of s, where s should be replaced by 2 by t 1 minus z inverse divided by 1 plus z inverse. So here t is equal to 1, therefore it is equal to 2 in bracket 1 minus z inverse divided by 1 plus z inverse. So therefore we can write h of z is equal to, we have 4 divided by s square is nothing but 2 1 minus z inverse divided by 1 plus z inverse square, plus we have root 2 root 2s, that is 2 root 2 into 2 in bracket 1 minus z inverse divided by 1 plus z inverse plus 4. Or I can write it as h of z is equal to 4 divided by s is replaced by 2 1 minus z inverse divided by 1 plus z inverse, this whole square because we have a square, plus 2.828 into 2, we have 1 minus z inverse divided by 1 plus z inverse and plus 1. So simplifying this further, I can write h of z is equal to, here now if I take 1 plus z inverse square as LCM, this will come on numerator. So I can write 4 in bracket 1 plus z inverse square, and on denominator I can write 2 square, that is 4 into 1 minus z inverse square plus 2.828 into 2, it gives 5.656. Here we'll get 1 minus z inverse, and another term is 1 plus z inverse. 1, here we'll get 1 minus z inverse 1 plus z inverse plus, at place of 1 it will be multiplied with 1 plus z inverse square, that is 1 plus z inverse square. So now I will try to simplify this further. H of z is equal to, on numerator we have 4 1 plus z inverse square divided by, here we have 1 minus z inverse square. I will open this bracket, that is 4 1 plus z power minus 2 minus 2z inverse, plus we have 5.656 minus 5.656 z power minus 2, plus we have 4. I will open 1 plus z inverse square, that is 1 plus z power minus 2 plus 2z inverse. So simplifying this, I can write h of z is equal to, we have 4 in bracket 1 plus z inverse square divided by, I will multiply these terms, that is 4 plus 4z power minus 2 minus 8z power minus 1 plus 5.656 minus 5.656 z power minus 2, plus we have 4 plus 4z power minus 2 plus 8z power minus 1. So simplifying this further, I can write h of z is equal to 4. Here I will write it as 1 plus z power minus 2 plus 2z inverse. On denominator side we'll get, here the constants are 4 plus 5.656 plus 4. So it gives 13.656, and here minus 8z inverse and plus 8z inverse will get cancelled. Remaining term is 4z power minus 2 minus 5.656 z power minus 2 and 4 z power minus 2. It gives plus 2.344 z power minus 2. Now I will divide numerator and denominator by 4. Therefore I can write h of z is equal to, so 4 by 4, its value is 1, so I will write it as 1 plus 2z power minus 1 plus z power minus 2 divided by, here 13.656 divided by 4, it gives 3.414 plus 2.344 divided by 4, it gives 0.586 z power minus 2. So this is the transfer function or system function of digital filter. Thank you for watching.